Hello everyone, I am Prantik Chatterjee, a PhD student from the Department of Computer Science and Engineering, IIT Kanpur. I will be presenting my work on proof-guided under-approximation widening for bounded model checking. This work was done in collaboration with Jaideep Singh Mehta from Oracle India, Dr. Akash Lal from Microsoft Research India, and Professor Shubhajit Roy from Department of Computer Science and Engineering, IIT Kanpur. The problem that we look at here is that of program verification. So essentially, given a program P and a property R, we would like to verify whether there exists an execution of P that can violate R. If there exists such an violating execution, then we say that P and R together is unsafe. Otherwise, we say that P is safe with respect to R. One of the more popular approaches for program verification is called symbolic model checking. In symbolic model checking, we encode the program into a logical formula P and we assert the negation of the property that we want to verify. So together this conjunct P and negation of the property R, this is sometimes called a verification condition or a VC. Next, we feed this VC to an SMT solver. Given a logical formula, the job of an SMT solver is to say whether it is satisfiable or unsatisfiable. Now, if the SMT solver says that the VC is unsatisfiable, so that means there does not exist any property violations in the program. Therefore, this program property pair is safe. Otherwise, the SMT solver returns an model which is an execution trace of P that violates R. Now, this VC can often grow too large to be handled by even modern SMT solvers. Hence, another way to do the symbolic model checking is called bounded model checking. So in bounded model checking, we unfold the recursive procedure calls and the loops only unto a certain depth. This essentially evaluates only a subset of program paths. Bounded model checking has been applied in program verification for a long time. One earlier approach was called static inlining. Static inlining takes as input a program P with a starting procedure main, and it says whether it is safe with respect to the property or if it is unsafe, and then in that case it will return an execution trace. So let's look at an example program. So in this program we have a starting procedure main. In the starting procedure we initialize two local variables xy to 0. We have a boolean variable. If the boolean variable is true, then we call some variable, we call some function foo on x. Otherwise, we call bar on x, and then we assert the negation of the property, which is y not equal to 0. We also show the function bodies of foo and bar here. In foo, again, if some condition is true, we call foo1, otherwise we call foo2. This foo1 and foo2 are very simple function which will simply increase, either increment or decrement the input by 1. Similarly, we also have the function body of bar here. If some condition is true, bar calls bar1, otherwise it will call bar2. The function bodies of bar1 or bar2 are again very simple. They simply increment the input variable either by 5 or decrement by 5. So I show the call graph of the function here. Main calls foo and bar, and foo calls foo1 and foo2, bar calls bar1 and bar2. In static inlining, we unfold the entire call graph and construct a gigantic VC. This VC is fed to the SMT solver and the SMT solver says unsat and therefore it is safe. The problem is, even in static inlining, since we are unfolding the entire call graph, the VC might become too large to be handled by solvers. So another approach was proposed, which was dynamic inlining, or more specifically stratified inlining, which was proposed in 2012. Stratified inlining is driven by a counter-example guided abstraction refinement approach, which is more commonly known as CR. Coral is a tool which implements the stratified inlining algorithm. Coral is a mature and state-of-the-art open source tool. It has been used by Microsoft to verify Windows device drivers. So let's take a look at the CGAR strategy. CGAR, this over approximation refinement, which is driven by counter example. Let's look at an overview. So in the left hand side figure, let's say we want to verify a program, and this green oval shows all the reachable program states, and this red oval shows all the error states in the program. So initially we start by constructing a over approximated abstraction of the program. This is showed by the outermost oval, which is the over approximated abstraction M1. So when we construct M1, we see that there exists an error state P which is reachable in the over approximated model M1. So we want to refine the over approximated model such that we can rule out this counter example P. So we refine it and we construct a new model M2. Again in M2, we see that another error state is reachable, which is Q. So we rule out this error state as well and we arrive at M3. Now in M3, we see that M3 is an over approximation of the original program. Therefore, all states that are reachable in the original program, those are reachable in the over approximated model as well. So essentially, M3 is a superset of the original program's behaviors. So if no error state is reachable in M3, so that means the original program is safe as well. On the other hand, in the right side figure, we see when we construct M3, an error state R is reachable in M3. And this error state R, this is a concrete error trace. Essentially, this means this R is a reachable program state for the original program. Therefore, we say that the program is unsafe. So let's look at an example how this cigar strategy works for the stratified inlining. So it takes an input, a program P with a starting procedure main, and again it gives out an outcome whether it is safe or unsafe. So we have our original program main. So to construct an over approximated model, we will over approximate the procedure calls. So there are two procedure calls here, foo and bar. To over approximate them, we make these outcomes y non-deterministic. So that means we havoc y. Now y can take any value. So if y can take any value and we try to search for counter examples which can violate this assert. So one counter example is that it goes through that counter example trace, it can go through the true branch of this if, and then it can violate the assert. So we'll have to define this over approximated model. To define it, since it goes through the true branch of if, we inline the procedure call here. So we call y equal to foo x, inline the procedure, but foo again has two function calls, foo1 and foo2. So foo1 and foo2 are over approximated. So in the first over approximation query, the counter example had foo, so we inline it. Next, in the second over approximation query, again we can find one counter example trace which can go through foo1. Therefore, we inline foo1 again. Similarly, we will find another counter example trace which will go through foo2, so we inline foo2. Similarly, next counter example trace will go through bar, therefore we have inline bar, and then we'll inline bar 1, and then we inline bar 2. In the last query, we see that whenever we fire a counter example trace, there exists no whenever we fire an over approximation query, there exists no counter example trace. Therefore, we say that the query is unsatisfiable and the program is safe. Now, this space of bounded model checking, this has long been dominated by cigar strategies. So we wanted to propose a complementary strategy, which we call under approximation widening. Let's take a look at a small overview how under approximation widening works. So let's say these outermost oval, these are all the reachable program states, and again this red oval is all the error states. Next, we construct an under approximated model of the program. So the under approximated model, this is essentially a subset of the main program's behavior. Let's say main had two call sites C1 and C2. So we block all executions through C1 and C2. So now this is a subset of the original program's behavior, that is an under approximated model. So once we get the under approximated model or the query, the under approximation query, it gives unset. So we want to take a look at why we cannot reach the error states. Now the reason that we cannot reach the error states, this will be given by the minimal unset code. So we take a look at the minimal unset code. The minimal unset code says that C2 was the reason that we could not have reached the error state. Therefore, we concretize C2, concretize or inline C2. And then, so this again gives us another under approximated model. So next we see fire another under approximation query by blocking all other call sites, and again look at the reason why we cannot reach an error state. We see that we cannot reach an error state because these C3 and C4 are blocking our way. Therefore, we inline them again. So after inlining C2, C3 and C4, we see that the error states are still not reachable, but now this constructs a proof. It says that in the original program, once we inline C2, C3 and C4, regardless of what happens to the other call site, it will still become, the query will become unsat. Therefore, it is not possible for us to reach an error state. Hence, the program is safe. On the other hand, after inlining C2, C3 and C4, if there existed an error state which is reachable in the underapproximated model, since the underapproximated model is a subset of the original program's behavior, then these R would have existed in the original program as well. So then we would have said that the program is unsafe and return this execution trace R. Again, let's look at a small example how underapproximation widening works. So it's the same program as before. We have these two procedure calls foo and bar, and now we want to block executions through all the call sites to make an underapproximate model. To make this an underapproximated model, we replace these two calls with assume false. Now, if we fire an query to the SMT solver, the SMT solver will say that this is unsat. So this assert is not satisfiable. Now, why is this assert not satisfiable? Because we have blocked the executions to block both these call sites. So we'll have to concretize them. So we widen the model by inlining these foo and bar. So in the first query, our unsat core contains foo and bar. We inline those. Next, foo and bar also had two call sites, foo1, foo2, bar1 and bar2. Hence, we underapproximate the model. Again, we get unsat. So the assert is not satisfiable. Unsat core says that foo1, foo2, bar1 and bar2. These four are the reason why we cannot satisfy the assert. Therefore, we inline these four call sites. Once we inline all these call sites, the next underapproximation query, so it will say that the assert is not satisfiable. So this constructs a proof of the program. So we say that the program is safe. So we implement our proof-guided underapproximation widening approach in a tool called Legion. To perform our experiments, we take test subjects from the SDE benchmarks, which consists of Windows device drivers, and we take the Linux device drivers from the SBComp benchmark suite. Out of all these benchmarks, we select only those benchmarks which are difficult for Coral to solve. That is, on these benchmarks, Coral takes more than 120 seconds. So there are total 727 such instances. Note that although these benchmarks are those on which Coral takes greater than 120 seconds, so there are many benchmarks on which Coral struggles. So that means Coral cannot even solve these benchmarks within even 2 hours. So our time budget for solving each of these instances, we set this time budget to 7 to 200 seconds. Our objective is to compare the verification time of Legion with that of Coral. So let's take a look at the results. This is a scatter plot. The scatter plot shows the verification time of Coral and the verification time of Legion. We plot the verification time of Coral on the x-axis and we plot the verification time of Legion on the y-axis. So notice all these benchmarks. These are all the benchmarks on which Coral could not solve these benchmarks within 7 to 200 seconds, whereas Legion did. And again, there are these benchmarks. They were not solved by Legion within 7 to 200 seconds. However, Coral was able to solve them. So we had a total of 727 instances. Out of the 727, 330 was not solved by any of these tools within 2 hours. And there were 212 instances which were solved by both the tools. Coral exclusively solves these 46 instances, whereas Legion exclusively solves these 135 instances. Now, looking at the scatter, it seems that there are a lot of instances on which Coral struggled, but Legion solved very easily. And again, there are a lot of instances on which Coral performed very well. It verified them very fast, but Legion could not. So we ask a question that if we can reap the best of both worlds, can we take the benefit of both the techniques? So to reap the benefit of best worlds, we propose a portfolio strategy. The portfolio strategy, we term it as Legion Plus. So Legion Plus essentially employs one instance of Coral and one instance of Legion to verify a given benchmark. Whenever one verifier finishes, it kills the other verifier and returns the outcome. So employing the portfolio verifier, we show the performance in this plot. So as we can see, the x-axis shows how many instances were solved, and y-axis showed how much within how much time. So this is time taken per instance. So if we look at cumulative time, we see that Coral solves 262 instances in total within 109 hours in total. Legion solves 351 instances within 112 hours in total. Whereas this portfolio verifier, Legion Plus, it solves 369 instances within only 71 hours. So note that Legion Plus employs twice as much as resources as these either Coral or Legion, since it is running two verifiers in parallel. Hence, to make the comparison fair, we allocate half the time budget of the sequential verifiers to Legion Plus. So to verify each benchmark, Coral and Legion gets 2 hours, whereas Legion Plus gets only 1 hour. However, if we allocated the same time budget of 2 hours to Legion Plus as well, it would have gone on to solve 397 benchmarks. So now let's look at a speed up. So we compared the speed up with respect to the benchmarks which all these tools have solved. So there were 212 instances which all of these tools have solved. So to solve these 212 instances, Coral takes 81 hours, Legion takes 52 hours, whereas Legion Plus takes only 28 hours. So Legion Plus is nearly twice as fast as Legion, and it is nearly 3 times as fast as Coral. So to conclude our presentation, we have developed a proof-guided under-approximation widening, a complementary strategy to CGAR. We have also proposed a portfolio technique Legion Plus to reap the benefits of both these complementary techniques. We demonstrate that the portfolio verifier Legion Plus is nearly 3 times as fast as the state-of-the-art verifier Coral. Legion and Legion Plus are both open source and they are available at the Legion branch at this following GitHub repository. Thank you.